During this section, we're going to be looking at using resources. This is content from Chemistry Paper 2. Firstly then, the first part of the specification, we need to know what actually our uses for Earth's resources are, and this tends to fall into a few categories. We use it for warmth, shelter, food and nutrition, as well as our transportation. So for the most part of the different materials that we're looking at, they tend to fall into one of these categories. The important aspect of where chemistry comes into this is that natural resources, so things like wood or wool, are supplemented by agriculture and also can help us provide food, timber, clothing and foods. In this section, we're going to be looking at using resources. This is part of your Chemistry Paper 2 content. We're going to talk about Earth's resources overall, and the first part of this topic is about how we actually use the Earth's resources. Now, typically this falls into we use it for warmth, shelter, food and transport. And what we find is that natural resources such as wool or wood, which are also supplemented by agriculture, are able to provide food, timber, clothing and fuels. When we look at using resources, there are some key words that we need to be aware of and able to use in our explanations. The first thing is that resources can be finite. Now these are resources that can only be used once and are in limited supply. So for example, we might be looking at metals here. Resources could alternatively be renewable, which means that it's been constantly replaced and we're not at risk of it running out. When we talk about sustainable development, this word of sustainability means two things. First of all, that we are able to meet our current needs, so the current generation, but that we are also able to meet the needs of future generations as well. So it's meeting our needs, but also ensuring that future generations can have their needs met too. So sustainable development is what we're really aiming for here. If something is unsustainable, this is a big underlying principle of things are going to run out. At some point in the future, it won't be available, and therefore the future generations can't meet their needs. So a lot of what we'll look at within this topic is around sustainable development and how we can work towards this. And it's where chemistry really comes in, because the chemistry itself can help improve agricultural processes, but also industrial processes that can help us move towards sustainable development. The next section of the topic focuses on water and this idea of potable water. Now this by definition is water that is safe to drink. By that, the microbial level is low, as is the salt level, and neither are going to cause harm to the person who consumes this. So it's looking for that combination of low microbe content and low content of dissolved salts. Potable water is not pure water. So it is made up of H2O, but there will also be other minerals dissolved in it. If we were talking about pure water, this would be H2O and nothing else. And we usually don't come across this unless we're collecting the condensation from distillation. One concept that's going to come up is we could be asked how we actually obtain potable water. And the first thing is we need to identify where our supply of water is coming from. Either our supply is coming from salty water and seawaters, or it's coming from fresh water, which is a reference to the lack of salt. If we have two available sources of water, due to the reduced processing and energy demands, we tend to use freshwater supplies as our first way of obtaining potable water before we look at getting potable water from salty water instead. So how do we obtain potable water from fresh water? This involves a couple of processes. First of all, we'll pass the water through filters, and the purpose of this is to remove any solids that may be suspended within. We will then sterilise this water, and we can use one of three possible chemicals. We can use either ozone, UV, or chlorine, and the purpose of each of these is to kill microbes. If we look at how we obtain potable water from salty water, this is now slightly different. We have to go through a process known as desalination, which is done by distillation. Now this means we're removing the salt. Now with this, we can also use a process known as reverse osmosis, which is using membranes and moving water from an area of high water concentration to low, which is a reference to the reverse. So with the distillation, this would involve boiling the water, collecting the condensate, and having that as our pure water. Or we can go through this process of reverse osmosis. In both of these methods, we're going to be using a huge amount of energy. Either we need to use energy to boil water and then collect the water vapour that comes from this, so a lot of energy needed there, or we need to use a lot of energy to get the water particles to move in the opposite direction from where they would normally travel. So from an area of low water concentration across to high. So be prepared in exams to talk about how we would make the following sources of water potable. So either we can use groundwater. In this, we'll first of all identify a source of water. We will filter this to remove solids. So there's our kind of point and our development. And we'll then sterilise to kill microbes. And here we can use UV, chlorine or ozone. Some questions might ask you what we could use to sterilise water. And generally what they'll do is give you 2 marks. So you do need to be aware of all 3 of these because it might be a shorter response question where we're just identifying a factor equal. With the salty water, this we can either go through reverse osmosis or we can use distillation. But in both of these processes, it's going to be more expensive. This is going to cost a lot more money because more energy is required to do these. This leads us on to our required practical, in which you could be asked how we can determine if water is pure. Now the idea here is that we'll add an evaporating dish to a balance and record its mass, because the container that we use does have mass to it. This isn't negligible. We'll then measure a fixed volume of water into our evaporating dish. So this might be, for example, just 5 centimetres cubed. We'll then use a Bunsen burner, and the purpose here is to actually evaporate all of the water. If you wanted to do this more gently, you'd actually add this on top of a water bath, so a beaker of water with this suspended on top. But we're going to heat this until all the water has been removed. Once that's done, we'll now re-weigh our container, because now if anything was left in that water, we should have trace remains around the side of our evaporating dish. When we re-weigh this, it should now weigh more. If the water sample was completely pure, we would find that the container, if it weighed, for example, 58.32 grams at the beginning, if the water was chemically pure, it would still weigh 58.32 grams at the end because all the water is evaporated. But if the substance was not chemically pure and some of the substances dissolved have remained on that balance, what we'll now find is that actually we're going to have an increase in mass. The next section starts to look at wastewater. Now with this, it's looking at how we process wastewater that's going down into the sewers so that it is actually safe to go back into our water supplies. So into that, for example, the river over here. Now, there are 2 main processes producing this wastewater. First of all, there's urban lifestyles. So this is a reference to homes and people domestically using water. So this is the water going down our showers, down our toilets, from our dishwashers and washing machines. But there's also industrial processes. So this is a reference to industry that might be using water and releasing waste. Now it's really important that this wastewater is safe to be released back into the environment, because linking this to biology, it would be devastating for the environment if toxins or things that shouldn't be in a water supply were added. Now, sewage and agricultural waste require the removal of organic matter. So we're looking here at solid like feces. It might also include leaves that have fallen into the rainwater as well, that have gone down the drains. But this also relies on the removal of harmful microbes, which have probably fed like mad on the organic matter. So they both need to be removed. Industrial waste is even harder to process because not only do we have all of that to remove, but there might also be harmful chemicals in that water that we need out as well. With this then, be prepared to talk about how wastewater is treated, and this is a potential 4-mark descriptive question that comes along. So first of all, the sewerage is screened so that the grit and any large stuff is first of all removed. So we're talking about branches, solid like metal cans that have come down that sewerage. Anything solid, hopefully at this point that's large, is removed. These screens are like large metal grills that this passes through, and it will enter into these pools and tanks. Now notice in this, it's kind of like the darkest over here. This is our sewage coming directly in, and then it moves from tank to tank as it gets cleaner and cleaner. But we're going to look at the processes that actually how this happens. So first of all, the wastewater goes through a process of sedimentation. So the water is pumped into this large tank and that's left to settle. All the solid stuff that weighs a bit more will over time drift and settle down at the bottom, while the water, the liquids themselves, will remain closer to the top. There are 2 sections now to our sewerage. There is a sludge. This is the thick stuff that forms at the bottom. This goes through a process of anaerobic digestion. This is at the bottom of a tank where there is a heavy microbial life presence. Oxygen levels will be low. And so anaerobically, without oxygen, this sludge will be broken down. The top part of this sewerage is known as effluent, and this will be biologically broken down aerobically. So this is actually broken down by bacterium, not necessarily harmful to us, but bacterium that break this down in the presence of oxygen. So we have anaerobic digestion of the sludge at the bottom, and the effluent is aerobically broken down by microbes. And this is a potential 4-mark question. That idea of sedimentation, what happens to the sludge, anaerobic digestion, and what happens to the effluents. So it's biologically, aerobically broken down. So the sludge is the semi-solid sewage that goes to the bottom following that sedimentation, and it's broken down anaerobically. While the effluent is the liquid sewage that's on top, and this is aerobically, biologically treated. In the next section of this topic, we start to look at alternative extraction methods for metals, and this is where the higher content only comes in. First of all, this relies on the idea that the Earth's resources are in very limited supply. And as part of this, what we know is that copper ores are overall becoming scarce, and we need new ways of extracting copper from low-grade ores. And this is where the idea of phytomining and bioleaching come in. These are both alternative methods to mining. And the issue with mining is, first of all, the rocks that we can physically dig up are getting scarcer and scarcer and scarcer. We've used the high-grade ores already. But that mining itself is problematic. This involves digging up and moving huge amount of rock. So the digging is destroying habitats. It's also incredibly loud, incredibly polluting, and not a potentially pleasant place actually to be living close to, and certainly not for organisms that have had their habitats dug up around them. So the first method involves phytomining. Now in this, we are using areas of land that have low concentrations of copper or metals that we'll be looking for. And the idea here is this is an area that's not particularly hospitable to crops, But what we will do is we'll use some plants to grow on that land. And we'll use them. They, through their root system, will absorb these metal compounds that are dissolved in the soil. So they'll absorb them through the root systems and take them into themselves, and they'll become part of the tissue. Once they've grown, we'll then go and collect the plants and we'll harvest them. So we'll cut them and collect. But we will burn their ash. So the plant has removed the metals from the soil, they've moved into the plant, and we now burn this, collecting the ash that forms from this. An alternative method is to use a process known as bioleaching, and this involves using bacteria instead to break down these ores to a solution containing copper ions. In this, if we have a solution, we typically have our bioleaching bacteria added to crushed rock in solution, and over time they'll make a chemical known as leachate, and this is really rich in the copper ions, so they're breaking these rocks down, making the copper ions come free. In both phytomining and in bioleaching, we ultimately end up with a solution of copper. So if we get that ash from phytomining and add it to water, we can form a solution of our copper salts. With the bioleaching, it's produced a leachate, which in itself has got copper ions in solution. Now this can be extracted in one of two ways. Firstly, we can get it by using displacement reactions using scrap iron. So for example, if I've got my copper sulfate in solution, so I can obtain this, either use my leachate or my ash from my burnt plants, and we add iron to this, because iron is more reactive than copper, it should displace the copper, producing iron sulfate and copper metal, which we can now go on to use and extract for whichever purpose we kind of see fit. And so there, for example, is the simple equation for this. Alternatively, we can extract this using electrolysis. Here, the copper ions are attracted to the negative electrode, and it's because they're opposite charges. Now, the copper ion here will have 2 electrons added back on, and so we say that they are reduced. And here the ion turns back into an atom and will form, at this point, copper. We might observe changes on the electrode itself. We should see a change in colour. This will literally turn more coppery in appearance, and its mass of this electrode should increase. We have this concept and idea of life cycle assessments, and these are carried out to assess the environmental impacts of any product at each stage of its life. We'll look at the resources that we're using for this. We'll look at the manufacturing, the packaging, how far we have to transport this, and actually when this product gets to the user, how long it lasts for. And we also look at how we get rid at the end of its life. All of these aspects are used to consider the impact that that product had on the world overall. Some things are really easily to quantify, and you might be given data in an exam question where you're asked to do this. So water we should see as a limited resource. We've seen earlier on that this takes processing to clean it, but also to make it potable. So the use of water, we can quantify how much water has been used, how much wastewater has been produced. The quantity of resources that we're using, how much energy has been used, they're all very easy actually to add a number to, so easy to quantify. However, some things become a bit of a judgment call. So sometimes we're looking at the effect of pollutants. It gets a bit what we say subjective and not purely objective. So sometimes it's looking at making balanced judgments, but it's not going to be a case that there's a number assigned. And so at that point, comparisons can get harder. What we generally tend to do though, if we're looking at a product, is we look at their life cycle assessment, look at the impact that they have. And you might be actually asked to do that in exam questions. But when we look at these, it can be very easy to sometimes misuse it. and kind of skew it towards one kind of point of view. Generally, when we're looking at resources, look at, are they renewable or are they finite? Because actually the life cycle assessment of a resource, if it is a renewable resource, it will have a much smaller imprint on this earth than a finite one. So if we're using crude oil in particular, that would normally be seen as quite a bit of a drawback there. Well, if we've got something that can be grown sustainably, it's a bit different. When we start to look at the end of life, we have this idea about reducing, reusing and recycling. Reducing is very much kind of what it says on there. But the idea of reuse, so the idea that a plastic carrier bag we would use again and again. So the hope is that every kind of bag we've got in the home, to be more sustainable, if it was used 20 times rather than once in its life, would make that a much more sustainable product. Recycle is when we take that material, we can, for example, melt it down and remake it into something new. We've got some different materials that it's important that we kind of reduce their use. So these materials, so metals, glass, even our clay ceramics, our plastics, they are all made from limited raw materials. What we also know is that to make each of these materials takes a huge amount of energy, and that's coming from limited resources, mainly crude oil. Also, when we go to obtain a lot of these materials, drilling for crude oil for plastics, our clay is going to involve mining, our glass is using a range, depending on the glass, a range of different chemicals that need to be obtained, and metals also mined from the earth. Getting this through quarrying and mining also has huge environmental impacts. This is going to be responsible for a huge emission of CO2, all the transport and technology that's needed to actually have that removal, and destroying habitats in the process. So some products like glass bottles, plastic bags can be reused. But also the glass bottles can be crushed down and melted to make different products also. Other products can't be reused. And so actually when we go back to recycle, this is taking a material, melting it down, and then using it for something different than what it was originally used for. So this involves melting and recasting, or it might mean reforming into different products. So if we were melting down a bottle and then reforming it into a new glass product, that would be an example of recycling. Separation tends to cause a bit of an issue in recycling. So when we look at recycling, we need to make sure that products are separated, because actually when we look at this, the material and the properties are really important in the final product. And so plastics, for example, are notoriously quite hard for some companies to use as recycled plastics, because the integrity and the strength of those plastics can be changed when we go to use it again. So be aware that when there is recycling, we have separation that's required, but that it can be tricky at times to make sure that the product we make out of recycled materials has the actual properties that we want. And so there are limitations there. So, for example, some scrap steel can be added to iron from blast surface, and this can reduce the amount of iron that needs to be extracted from iron ore. So it's one way we can kind of reduce our use of materials there. For separate sciences then, we need to know what corrosion is. And this is a destruction of materials by chemical reactions with substances in the environment. And rusting is an example of corrosion. Now, for rusting to occur, we need both air and water for this to happen. But it is, as I've said, an example of corrosion. We can prevent corrosion in a few different ways. First of all, we can apply a coat that acts as a barrier, so paint or even sometimes like an oil can be applied. This is going to prevent both water and air getting into contact with that metal. So greasing and painting are both examples of this. As is electroplating, so this is placing another metal on top. Some coatings are actually reactive, and the idea here is that we have an idea of sacrificial protection. So for example, if we add zinc and attach it to iron, The zinc will react first before the iron does. If we look at aluminium, aluminium, for example, has got an oxide coating that protects it from further corrosion. So the aluminium that we see isn't actually aluminium. We're looking at aluminium oxide, but that has formed a perfectly impermeable layer where no oxygen or water can get through that single coating of aluminium oxide to the aluminium underneath. Alloys are a really useful material, and these are mixtures of metals, and we have them in the correct proportions with other substances to give the properties that we want. So bronze, for example, is an alloy of copper and tin. Brass is an alloy of copper and zinc, while golds can be alloys that are with silver, copper and zinc, and they'll give different appearances. When we talk about gold, pure gold is 24 karat gold, while 18 karat gold is 75%. 12 karat gold would be a half and half, so 50%. Steels are one big example of alloys though as a useful material. So steels are alloys of iron that will contain other elements including carbon and sometimes other metals as well. High carbon steel has carbon present along with the iron. It's very strong, but it is brittle. While low carbon steel is softer and it's more easily shaped. If we've got steels that contain chromium or nickels, these are what we call stainless steels. They're really hard and they're really resistant to corrosion, so they're not going to react. Another set of materials are ceramics and composites. So for example, if we look at glass, most of the glass we use tends to be what we call soda lime glass. And we use, or make this I should say, by heating a mixture of sand, sodium carbonate and limestone together. An alternative, however, is borosilicate gas. An alternative, however, is borosilicate glass. And this is made also from sand, but it's combined with boron trioxide. Compared to soda lime glass, this is going to melt at far higher temperatures. Clay ceramics can include pottery and bricks, and these are going to involve shaping wet clay into the shape that we're after and then heating in a furnace. When we look at these materials, we also need to be aware of polymers, which we've covered in previous topics. Now, the properties of polymers themselves depend on the monomers that went into them, but also the conditions that they were made. So if, for example, we look at polyethylene, the monomer for both of these was ethene, made in addition polymerization. But we've got low density and we've got high density polyethylene. Low density polyethylene has this branching on them, and this is holding those chains apart from each other. This reduces the strength of the forces in between these chains and so lowers the melting point. While here, with the high density polyethylene, we now have minimal branching. The chains can get really close together and have really strong forces between them as they're closer, and that will raise the melting and boiling point. But these are both made originally from polyethylene, or polyethylene I should say, is made from ethene, but they're two different versions of polyethylene. Polymers can also be either thermosoftening polymers or thermosetting. Thermosoftening, when heated, so thermo, they will soften. This is because the chains are all in isolation. They're not actually connected to each other. So when this does have a heat applied, the chains just start to move away from each other. When we look at thermosetting polymers, these do not melt when they're heated. And that's because now, if we have a look, the chains are attached together by these side branches. These are bonds. These are very, very strong covalent bonds. And so when we heat this, those bonds do not break. The chains remain in place. When we talk about composites, These are materials that are made up of these are substances made up of two or more materials that have different properties. Overall, they're combined to give a material with better properties. Typically, there are two components to a composite. We've got a matrix, and this surrounds and binds fibres together. And we've got the reinforcement. This is the fragments or the fibres that we'll use. Examples of composites then include reinforced concrete. So we've got a concrete, that's the matrix, but the reinforcement here is the iron grid within. And it provides a much stronger concrete than just concrete on its own. We've also got fiberglass. So our reinforcement here are the fibres that we can kind of see waving through that structure, while the matrix is the material that binds this all together. We've also got chipboard, and carbon fibre is another example of this also. In the final section of the chemistry paper 2, it starts to link in the Haber process, how we make ammonia and what we use this ammonia for. So first of all, the Haber process is the chemical reaction in which we make ammonia. And ammonia in turn, NH3, is used to produce nitrogen-based fertilisers, which are vital for plant growth. So the raw materials for the Haber process are nitrogen, that's coming from the air, and hydrogen. Now hydrogen we obtain from natural gas, while as I said, nitrogen comes from the air. Now these react, and you need to be aware of the conditions. So that purified gases are passed over an ion catalyst. This happens at a high temperature and a high pressure of around 2,000 atmospheres. So you need to know the high temperature of 450 degrees and the high pressure of 200 atmospheres. What should then happen is that some of the hydrogen and ammonia, or some of the hydrogen and nitrogen, will react to form ammonia. But the reaction is reversible. So actually what can immediately start to happen is the ammonia then breaks back down into nitrogen and hydrogen. So what happens is that we start to cool this. So we cool this and liquefy the ammonia and remove. And that should slow its decomposition back down into nitrogen and hydrogen. Any of the unused gas, if we notice, is taken in and recycled and brought back round. A very common exam style question is to be asked why we use these conditions. And this really pins into the fact that the Haber process is reversible. So, with the reaction, ammonia's breakdown is endothermic. And so, if temperatures are high, ammonia will break down really quickly. So, actually, if we go back here, the reason why ammonia is cooled is because if it's cool, it won't have the energy to turn back into nitrogen and hydrogen as quickly. So, ideally, we want cool temperatures for this reaction. The warmer it is, the more the ammonia will break down. But 450 degrees isn't exactly cool. If we actually put this at a low temperature, so ammonia doesn't break down again, the rate of reaction between hydrogen and nitrogen will be so slow it wouldn't be economically viable. And so the 450 degrees is taken as a compromise. Here, the particles have enough kinetic energy in collisions where the reaction happens fast enough, but it's not too hot that all the ammonia is then immediately breaking down. So we say this temperature of 450 is an optimum. We want the temperature low to prevent the breakdown of ammonia, but it can't be too low, otherwise the reaction just happens too slowly. Now with the 200 atmospheres, the higher the pressure is going to be, in theory, the higher the yield of ammonia should be. However, we can't just keep increasing the pressure higher and higher, because as we do so, it's got a consequence. To actually obtain that high pressure is expensive, but it also becomes more dangerous. And so, although a higher pressure would give us a higher yield of ammonia, we don't go as high as like 1,000 atmospheres because it gets too dangerous. There's got to be that compromise of actually the safety cause of concern here. The catalyst is used because it lowers the activation energy of the reaction. It will reduce the time it takes for equilibrium to be reached, and so we get a reasonable yield in a shorter time. That then leads us on to ammonia has been produced. This leads us on to NPK fertilisers. The N is standing for nitrogen, the P is phosphorus, and K is potassium. And these chemicals are needed to improve agricultural productivity, so how much crops will grow from that soil. Now, NPK fertilisers will contain compounds of all three of these. And where these nitrogen, phosphorus, and potassium is coming from is obtained in several different reactions. One important link, though, to prior topics is that NPK fertilisers are an example of formulations. The proportion of nitrogen, phosphorus, and potassium will be in the correct percentage for the properties that we want from that fertiliser. So, first of all, the ammonia that we produce during the Haber process can be used to make ammonium salts, which we can just directly add to our soil. We can also use it to make nitric acid. We can also obtain potassium chloride, potassium sulfate, and phosphate rock directly from mining. So we're digging these out of the earth. Now, so we've got a couple of rocks or salts here contain potassium, and we've got phosphate rock also. Phosphate rock needs no further processing. We can simply just add this directly to our fertiliser. Or alternatively, what we can do is we can treat this with nitric acid or sulfuric acid to make soluble salts that can also be used as fertilisers. Be aware of these. There have been some sneaky questions in the past. So, acid added to phosphate rock. If we add nitric acid to phosphate rock, we make calcium nitrate and phosphoric acid. And this is what we'll be then adding to our fertiliser. If we add sulfuric acid, we'll make single superphosphate, which is a mixture of calcium sulfate and calcium phosphate. If we add phosphoric acid, we'll make triple superphosphate, which is made up of calcium phosphate. And do learn these as factor equals.